When you're doing questions that involve trigonomic functions, you may find that the expression involved actually has more than one type of function, so it has a combination of sines and coses and tans, or maybe just multiple examples of the same function. If we were looking to solve such an equation, you would need to condense this down into a single function. And so in order to do that, we may need to look to something called trigonometry identities. Now these are rules that we can use where if we have certain combinations of the functions present, we can say that's the same as a different and hopefully simpler function. Now to be clear, this video is not going to be necessarily about solving of these functions themselves. That will be in a separate video. This here is just looking at how we can simplify the expressions at the beginning to get us to the stage where we can solve. So the first identity we may wish to look at is sin x over cos x. If this angle within each function is the same as each other, so it's like sin 40 over cos 40, we can say that this is the same as tan of that x, so in this case that would be tan 40. Can't do it if it's a different angle, but can if it's the same. Additionally, if there are any coefficients in front of these, so say it was like 6 sin x over 2 cos x, you would simplify whatever that would be as a fraction in front. So say 6 sin x over 2 cos x, 6 over 2 would be 3, and sin over cos is tan, so that would be 3 tan x. And then next, we also have that sin squared x plus cos squared x equals 1. Once again, this has to be for the same x value, and in this case, it does have to be the same coefficient. So if it was like 2 sin squared x plus 2 cos squared x, then that would be equal to 2, because if you factorize the 2 out, it's 2 lots of the sin squared plus cos squared. This formula we actually may be more likely to want to rearrange. For instance, we can use it to say that sin squared x equals 1 minus cos squared x, or that cos squared x equals 1 minus sin squared x. That any one of these three forms could be just as applicable to a question. It all depends on whether, if you already have 2 sines and squareds and cos squareds, do you want to eliminate them both to just leave you with a simple 1? Or if you have a sine squared, but the rest of your equation is all in cos, you can use this identity to turn that sine squared into a cos squared, and vice versa with the other version. Now you may still then have to deal with that maybe because you have a squared here, the other functions aren't squared, so maybe now have some cos squared plus cos plus something. We'll deal with that in a little bit, but yeah, to start off with, just switching between squared functions. As it happens, there's actually even more that we can do with this identity. But before we discuss that, we should turn to what's up here. If we were to have 1 over sine x, we could actually express this as another separate function. 1 over sine x we can call cosec x. 1 over cos can then be called sec x. Yeah, so it's the one usually begins with c, switches to become an s, and the one that usually begins with s switches to become a c. It's a little counterintuitive, but there we go. And then 1 over tan x will become cot x. So again, when we're looking to solve eventually, you will know how to solve for sine, cos, and tan. So maybe if you're starting with an equation that involves cosec or sec or cot, use these to work backwards to get you in terms of the other thing. Now that we have these, we can mention the other forms of what we do with this identity. Rather than just like moving things left and right around the equal sign, the other thing we can do is divide by a constant term. Let's say to begin with that we divided by cos squared x. So you'd end up with sine squared x over cos squared x plus cos squared x over cos squared x equals 1 over cos squared x. If sine over cos is the same as tan, then sine squared over cos squared equals tan squared. Or cos squared divided by cos squared, anything divided by self is just going to end up being 1. And then here, if 1 over cos is sec, then 1 over cos squared equals sec squared. This then is the equivalent equation that involves tan squared. It's not just used for sine and cos. It's only if you do this, you're going to be getting in sec rather than sine and cos, which if you wanted, yep, you could turn back into 1 over cos and so forth. Could of course do it the other way as well. So if we instead divide everything by sine squared, so sine squared x divided by sine squared x plus cos squared x over sine squared x equals 1 over sine squared x. As before, sine squared over sine squared, anything divided by itself is 1. If sine over cos is tan, then cos over sine is 1 over tan, which we can call cot. So cos squared over sine squared, 1 over tan squared equals cot squared. And here, if 1 over sine is cosec, then 1 over sine squared is cosec squared x. Just another identity that can also now involve these other two. We can call them reciprocal trigonomic functions here, because reciprocal means 1 over. To end off with this first just explanation here, you then come to what may be called addition formulae. So let's say if we were to have some coefficient of sine, but then within the brackets it was actually two things added or minus together, so the angle plus or minus some other thing, we could expand this to say it's the same as r sine theta cos alpha plus or minus r cos theta sine alpha. So just an example, if we were to have like 5 sine theta plus 30, that would be the same as 5 sine theta cos 30 plus 5 cos theta sine 30. With this in mind, we can actually use this kind of expansion to more often go the other way, to simplify all of these multiple functions that have been times together, simplify them down into a single sine function. What just may be required is to identify, what is the r and the alpha before we can write it in here, theta then just remaining a general theta. We'll get on to an example of how we can do that in a little bit. However, here, once you have this expansion, once we understand that this is how this can be done, we can actually use it for a very special version. If we were simply to say sine of 2 theta, so this is where r is equaling 1 and alpha is also equaling theta. So it's 1 sine theta add theta. This, therefore, would become sine theta cos theta plus cos theta sine theta. In other words, 2 sine theta cos theta. This is the double angle formula for sine, saying if you have sine of 2 theta, you can expand it to be this. You may use this if some terms in your equation have 2 theta, but others only have a single theta. Remember, these identities from up here only work if it's the same x or theta value in the angle, so you couldn't do like sine 2 theta divided by cos theta. They'd both have to be in single thetas or both be in 2 thetas. Or alternatively, if you started with these like cos and sine times together, you could reverse this to get it into a single sine function, where then the coefficient is halved and the angle is doubled. In a similar vein, we can now look at if this was r cos theta plus or minus alpha. Starts off sort of the same way. We're going to start with r, but that's going to be cos theta, and now cos alpha as well. Whereas in the sine addition formula, it was one of each in each term. Here in the cos, they're both causes of the cos theta, cos alpha, and then, whereas in sine, the plus or the minus was the same on either side of the equal sign, here, it's the opposite. So if it's a plus on the left-hand side, it'll be a right on the minus side, on the right side, and if it's a minus on the left side, it'll be a plus on the right side. Then we have r sine theta, and sine alpha. So once again, just as an example, if say we had 6 cos theta minus 45, we could say that's 6 cos theta cos 45 plus 6 sine theta sine 45 minus here, so plus here. And once again, if we were trying to get this into this condensed form, we'd just have to identify what is the r and what is the alpha. Again, example will be given in a minute. As with the addition for the sine, though, we can once again do a double angle for the cos. So cos 2 theta, where again the r is 1 and alpha is theta. Here, therefore, plugging it into this formula, you'd end up with cos theta minus sine theta minus, because to get 2 theta would be theta add theta. So this will be the same as cos squared theta minus sine squared theta. Okay, so if the squareds are added, it's equal to 1, but if they're minused, it equals cos 2 theta. Just tying back to this previous identity though, this actually allows us to now rewrite this one in more forms as well, just as we rewrote it earlier. Alternatively, we could say that cos 2 theta will be the same as 1 minus sine squared theta minus sine squared theta, because from here, cos squared is the same as 1 minus sine squared. So this will be the same as 1 minus 2 sine squared theta. So therefore, if you wanted, you could say 2 sine squared theta equals 1 minus cos 2 theta. So let's say that, it's another way of turning a sine into a cos, or maybe again, you have this 2 theta here, but you don't want it in terms of 2 theta, you want a single theta, plus the other terms in your expression have been in sine, so it's just another way you can convert between them. Similarly, cos 2 theta could also be called cos squared theta minus 1 minus cos squared theta, because sine squared is the same as 1 minus cos theta, or cos squared, sorry. Just expanding these brackets, cos squared minus cos squared is now plus 2 cos squared theta, and that's just minus 1. So 2 cos squared theta is the same as 1 plus cos 2 theta. Some of these may be given in a formula booklet in kind of their base form. Others you may just have to be familiar with how to derive. So these further ones are in black. You're going to have to rearrange for yourselves. But like the initial addition formulas and so forth, you may be given. Even so, you just want to be familiar with how you can use them. And for that, we're now just going to go through some practice questions. Usually at this stage, first we'll get you to do a question on your own, and then we'll go through a printed question together. However, this time, because this first section has been a lot of explaining, and there's a lot of concepts at play, we're actually just going to look at some various questions all together. If needs be, you can just rewind to look at the previous screen. And in general, I would ask that you try to have a go at this on your own, so pause the video, work these through one by one. But either way, we're just now going to go through them together, so pause if you want, and if you do, press play when you're ready to compare. Alright, so in question 1, we have that 3 sine squared x plus 7 sine x equals cos squared x minus 4. I want to show that that could be written in the form of 4 sine squared x plus 7 sine x plus 3 equals 0. Well, first notably is that while this has a combination of sine and cos, this is all in terms of sine. So we want to turn this cos squared into an amount of sine, or specifically, we can make it sine squared, because we can say that cos squared x is the same as 1 minus sine squared x, and still minus 4 afterwards. And then once we have this, all we have to do is move everything onto the left-hand side because we need it to equal 0 on the right. So if we had 3 sine squared x plus this additional sine squared x, because when it moves over the equal sign, its personal sign changes. So minus here, so comes a plus there. Still got your plus 7 sine x, and then we'll have a plus 4 and a minus 1 equals 0. So 3 sine squared plus sine squared is 4 sine squared, 7 sine is still 7 sine, and 4 minus 1 gets us 3. Now once we are in this form, if we did want to solve, we'd actually have to treat this like a quadratic and factorise, because right now we've got multiple sine terms and they can't be combined because one is squared and one is not. As I say, the solving is going to be left for another video, but just say at this stage, yeah, you would treat this as quadratic and try to factorise. Moving on to question 2, we have cos x over 1 plus sine x plus 1 plus sine x over cos x. Show that this is the same as 2 sec x. Well, whenever we're going to be adding fractions, we need to make them the same denominator. And the easiest way to make the same denominator is to times the two together. If, however, you times the denominator by something, you have to times the numerator by the same thing so as to keep the same value of the fraction. We don't actually want to change the value. So, if we were to be timesing this denominator by cos x, this cos x would be times by cos x as well, giving us cos squared x on the top, and then on the bottom, that 1 plus sine x, and then cos x. We could times this out if we wanted, but actually for the sake of some simplification later, I'm going to keep them in 2 separate brackets for now. Then we'll add to this, so we're now going to have 1 plus sine x times by the 1 plus sine x, so it's basically squared. So 1 times 1 will be 1, 1 times sine x is sine x times 1 is sine x, so together that's plus 2 sine x, and then sine x times sine x will be plus sine squared x, and again this is going to be over the 1 plus sine x times by cos x. Now, when you're going to be adding these together, because it's now in the same denominator, you literally just add the tops together. Cos squared add sine squared, that's just going to equal 1, right, from one of the identities above. And so 1 add 1 is going to be 2. And then here you still have your plus 2 sine x. And again, this is still over 1 plus sine x cos x. What we can do here is to say that this, if we just factorise 2 out the top, is now 2 lots of 1 plus sine x over the 1 plus sine x cos x. 1 plus sine x cancels with 1 plus sine x, leaving us with just 2 over cos x. And if 1 over cos x is sec x, 2 over cos x will be 2 sec x. Question 3. Express 3 cos theta plus 4 sine theta in the form r cos theta minus alpha, where r and alpha are constants, r is greater than 0, and alpha is between 0 and 90 degrees. Hence find the maximum value of that expression with the smallest positive value of theta for which this maximum occurs. So, to start off with, we'll see already this is going to be in this addition formula here. So what I'll actually do is just rewrite out what the formula is so that we have it to compare to. So it'll be r cos theta cos alpha. Since it's a minus here, it'll be a plus r sine theta sine alpha. Now what we do in these cases is we're going to compare this formula to what we've been given. Now if we look at the right-hand term first actually, I've got 4 sine theta here, and we're saying, if we can put it in this form, that that must be the same as r sine theta sine alpha. Well, we've already got the sine theta accounted for, but if these are the same, the r sine alpha must therefore be the same as this 4. They must be representing each other by providing the same value. Similarly, looking here, we've got a cos theta accounted for, but this r cos alpha This is in place of this 3. So r cos alpha must equal 3. From here, what we can do is we can divide these two expressions. R divided by r is just going to cancel, and sine A, or sine alpha over cos alpha, is going to equal tan alpha. So tan alpha equals 4 over 3. So alpha is going to equal tan inverse of the 4 over 3, which if, let's say, we go to 1 decimal place, will be 53.1 degrees. Using this, we can now just get our value for r by plugging it back into any previous part. So let's say that r is going to equal 4 divided by sine alpha, so this alpha value here, you get it equaling 5. Therefore, now that we know our r and our alpha, we can express this in this form by saying that it's 5 cos theta minus 53.1. With this, we can therefore comment on when the maximum value of this, or what the maximum value is going to be, and when it's going to occur. Cos and sine oscillate between 1 and minus 1. They cannot go above 1, they cannot go below minus 1. Therefore, the maximum value of the cos function, regardless of what's in the bracket, is 1. And 5 times the maximum of 1 is just going to be 5. So the maximum value of this expression here is 5. And then, if we think about what the smallest value of theta is, where that's going to occur, well, if we think to the trigonometric graphs, which if we're not familiar with those, again, I'm going to suggest looking at the video on how to solve these trigonometric functions, both because of how related it's been so far, and also, again, the graphs are going to be definitely covered in that one. If you were to find when does cos equal 1? Well, it equals that when it's the cos of 0. What value of theta would make theta minus 53.1 equal 0? Well, that would be if theta was 53.1 itself. Question 4. So starting from the formulae for sine a plus b and cos a plus b, prove that tan a plus b is tan a plus tan b over 1 minus tan a tan b. So here we can see we may have to derive the addition formula for tan. Unlike the sine and the cos, I don't believe you should be expected to know this one. At the very least, to see here, you can derive it. That is the case with a few things regarding tan. In another video on differentiation, where the differentiation of some trigonometric functions is involved, you may be expected to know about differentiating sine and differentiating cos, but differentiating tan, that is or should be given in the formulas where tan differentiates to sec squared. Here though, if we were to start off with this, so if tan is the same as sine over cos, then tan a plus b will be the same as sine a plus b over cos a plus b. So the expansion of sine a plus b will be sine a cos b plus cos a sine b, and that is going to be over, then for the cos expansion, so cos a cos b now minus sine a sine b. At this stage, somewhat like some of the other rewritings of formulas we've done above, we're going to want to divide by a constant value. With these kind of proving of identities and stuff, this is more like a step you're just expected to be familiar with and remember, rather than necessarily spot yourself. But what we're going to do is we're going to divide each individual term in both the numerator and the denominator by cos A, cos B. So you're going to have sine A cos B over cos A, cos B, and cos A sine B over cos A, cos B. And this will all be over cos A, cos B over cos A, cos B, and this will be minus sine A sine B over cos A cos B. Now this is a lot of fractions within fractions and functions multiplied together, but as we may spot, we now start getting things that cancel. Cos B here is going to cancel with the cos B here. Cos A is going to cancel with the cos A here. All of the cos A and cos B are going to cancel with each other here. And then this one, so far on the right, stays as is. But what this has meant is we're left with sine A over cos A, which from the identity is just tan A, plus sine B over cos B, which is just going to be tan B. Then on the bottom, if all of these are cancelled with each other, that just leaves you with a 1, and then minus this sine A sine B over cos A cos B, you can think of as sine A over cos A times sine B over cos B. So sine A over cos A is tan A, and sine B over cos B. We have now ended up with the fraction from above. And again, if potentially you needed to use this to rewrite certain tan expressions, maybe you have two types of tans involved in the question, two different types of angle, you can combine them into a single tan term. However, because of how more complicated this fraction is, unless the question was very much framed around using this specific identity, I doubt it should be necessary. For question 5, we now have prove that 1 over sine 2 theta minus cos 2 theta over sine 2 theta equals to tan theta. Well, we have two fractions that we're going to be minusing from each other. They're already over the same denominator, so we can just combine them together straight away. So it becomes 1 minus cos 2 theta on the top over your sine 2 theta. Because these are 2 thetas, we can expand them with the double angle formula. So this will be the same as 1 minus cos squared theta minus sine squared theta. And that'll be over 2 sine theta cos theta. Simplifying on the top here, we could replace the cos squared with 1 minus sine squared. So 1 minus 1 would disappear, and then you have minus sine squared is minus 2 sine squared, minus 2 sine squared would just be 2 sine squared theta over your 2 sine theta cos theta, and then cancelling through, the 2 will cancel with the 2, this sine will cancel one of the signs here, leaving us with just sine over cos, which we know from our identity to indeed be tan. Question 6. Express 3x plus 2 cos x in the form of r sine x plus alpha, where r is greater than 0 and alpha is between 0 and pi over 2. And then hence find the greatest values of that expression to the power of 4. Like we did above, I'm actually just going to write out the expanded form first, just so we can compare. So it'll be r sine x cos alpha plus r cos x sine alpha. Comparing here, so we have our cos x, but we're missing the 2. Instead, we've got r sine alpha. So this r sine alpha must be represented by the 2, must equal to. Here we have the sine x, so, but not the 3. So this r cos alpha must equal the 3. If you divide them by each other, you end up with tan alpha being 2/3. So alpha is going to be inverse tan of the 2/3. As we do this though, we must just remember the bounds for alpha, so it's between 0 and pi over 2. The fact that a pi is involved is telling us that this angle is in the unit of radians. So set your calculator into radians first, then put all this in, and that should get you an angle of approximately 0.588. Now that we have the alpha, we can use that to work out r. So r is going to equal 2 over sine of that 0.588, and that will get you an R value of root 13. Your calculator may well give this to you instead as a decimal, so 3.6 and so on and so on and so on, but for the sake here, I'm just going to give it in a surd form. Therefore, we can give this expression, this 3x plus 2 cos x, in that R form as root 13 sine x plus 0.588. And now that we have this, we can find the greatest value of that original expression to the power of 4. The maximum value is going to be based around what the maximum value of that expression would be. So, like with the question above, the maximum value of sine is 1. So, regardless of what's in the brackets, this will happen when it's 1. And that then is 1 times root 13. So, root 13, but this is then to the power of 4. So, root 13 squared is 13. Square that again, you get a maximum value of 169. Question 7 down here. Show that 4 cos x squared 2 theta minus cos x squared theta equals sec squared theta. Well, with these questions where you have your cos x and your secs and so forth, I would suggest rewriting these in the more recognizable forms of sine and cos. So this here would be 4 over sine squared 2 theta, then minus 1 over sine squared theta. These we can now try to rewrite and simplify slightly. So sine 2 theta, that would be the same from our double angle formula as 2 sine theta cos theta. So then sine squared 2 theta is that squared in the denominator minus the 1 over sine squared theta here. Expanding this bracket here, you end up with 4 over, now 2 times 2 will be 4, and then sine squared theta cos squared theta minus the 1 over sine squared theta. Here, the 4 and the 4 are just going to cancel to give us 1 here. Now, we're closer to having these as the same denominator, because when we're minusing, we need a common denominator. There was no way of doing it while you had a 2 theta and a single theta, but now they're all in single thetas. Both denominators already have a sine squared, so all this right-hand one needs is an additional cos squared. So we'll have 1 over the sine squared cos squared minus cos squared over sine squared cos squared. The 1 minus cos squared, that's the same as sine squared once you've combined them together. Again, that's over your sine squared cos squared, at which point sine squared cancel with sine squared to leave you with 1 over cos squared, and that, if 1 over cos is the same as sec, 1 over cos squared will equal sec squared. With that, then finally, we just come to this. Without using a calculator this time, find the exact value of sine 22.5 plus cos 22.5 squared, and you must show each stage of your working. Now at this stage, looking at this, maybe at first we would want to create some kind of addition formula. So say, okay, find what 22.5 is made up of by either adding things together or taking them away. But none of the values you may be expected to know for the trigonometry, or that you would know, can be used to make that. So instead what we're going to do is we are going to deal with the squared. We're going to expand the bracket. So sine 22.5 times sine 22.5 is going to be sine squared 22.5, then plus, so sine times cos will be sine cos, cos from sine will be the same thing, so together you've got 2 sine 22.5 cos 22.5, then finally cos times cos will be cos squared 22.5. Now, because this angle in here are the same, we can just think of it as sine squared add cos squared. So that's going to simplify to 1. And then here, if you have 2, then sine times cos, well, again, the angles are the same as each other. This is where we can employ the double angle formula in reverse. So we can say that that would be the same as plus sine. And then, because it will become sine 2 theta, 2 times 22.5, that is going to give you sine of 45. Now, sine 45 is one you may be expected to know, where that is the value of root 2 over 2. If you're not sure about this, once again, I'll recommend anyway going to the video on solving for trigonomic functions. Among that will be listed what few angles you may be expected to know the values of. Either way though, here, that is how you would come up with an exact value. Exact value means keeping it in surd form. Decimal would inherently be rounding, so that wouldn't be exact. That's the answer you would get here. Hopefully, this has all made sense. There's a lot of information on the screen, obviously, but I just wanted to show this as an example of the variety of ways we could employ these different identities. More practice will be done with them as they do appear in other videos, because with the A-level maths, you start ending up with concepts crossing over with other concepts. But until then, yeah, hope we're all good with this. And again, just once more, I would advise you go on to that video on solving the trigonomic functions so that you can then come to a trigonometry question and be able to complete it in its entirety.